So,
Hello.
Dr. Hemingway, thank you so much for coming on.
Thanks. No problem. You can
Yeah.
call me Doug.
Doug, awesome.
If that's comfortable for you.
No, yeah, for sure. How you doing today?
Good. Just ran over from a seminar. We had a visiting speaker over in the PMA building. So.
Yeah. Are you running that whole?
No, I was just the host. I was the person who knew this person and reached out to him and invited him. So I'm kind of looking after his schedule for the day and making sure he has lots of fun, interesting people to talk to and take him to lunch, take him to dinner later, stuff like that.
And if I'm remembering correctly, you had a proposal that you just submitted, right?
Yeah.
Yeah. How did that go?
I think it went well. It was due February 1st, so that's done now, and now I just have to wait maybe 3, 4, 6 months to find out whether it gets funded.
Yeah. Is that like a typical waiting time for?
Yeah.
Yeah.
And then we'll see. So I mean, I'll work on other projects in the meantime, and if that does come through, that funding does come through. I mean, it's probably a project I'll want to do at some point anyway. But if the funding does come through, then it should maybe influences the timing of when you do things. So if it doesn't come through, I might work on something else first and then come back to that later. Yeah.
So, to get started, I'd like to spotlight that from the outside looking in, your academic journey is really freaking cool. So from my understanding, and feel free to correct me at any time if I'm wrong, because you're obviously the expert in Dr. Hemingway's life. But you started your academic journey with robotics and systems design engineering at the University of Waterloo in Canada.
Right.
There you performed undergraduate research on autonomous drones, super cool by the way, which led you to a master's program at the International Space University in Strasbourg, France. And then after that, you spent a year in Sagamihara, Japan as a graduate intern, then came back to the States, got your PhD at Berkeley, went to Carnegie, and then worked in industry for a while at Maxar Technologies, and now you find yourself here at the University of Texas. Is that
right?
All accurate?
That's mostly right, but
Okay.
I mean that's very good because it's a very complicated journey.
Yeah.
So it's okay if it wasn't exactly right. So the thing that's missing is, so I did undergraduate degree in engineering, and then I went straight to work in industry. Originally, I had no interest in grad school. I wanted to go straight to work.
Okay.
And after undergrad, I went to work for a space robotics company, like the big one in Canada, the one that made the Canadarm. And I worked there for basically 8 years. So I had a whole 8-year career in space robotics. And then it was only towards that, 8 years into that when I started thinking maybe I could learn about some other things and kind of expand my horizons. And that's when I went to International Space University, and my internship at the Japanese Space Agency was sort of part of that. So I was only there for 3 months in Japan, but yeah, otherwise, it's a complicated and unusual journey for sure. So
yeah, I was amazed by how many places you went and how many places you spent time in. Yeah. And is it safe to say that planetary geophysics was not on your radar when you were going into undergrad?
Yeah, that's very safe to say. I don't know if I had ever heard of those two words together before. I guess like a lot of people, I was probably interested in space exploration and space science, but I didn't know too much about it. But I kind of gravitated towards engineering, and then I was an engineer. And like I said, I wasn't even interested in grad school at all at the time. I thought I would just go right to work and start building stuff. And then my interest in robotics kind of led me into, thought it was a good way to combine a lot of different disciplines of engineering. So I did robotics research in undergrad. Mm-hmm. And then I was like, okay, well, I'm still interested in space. So how can I do space and robotics? And there's this space robotics company. Have you heard of the Canadarm? It's the big robotic arm on the space shuttle and then also on the space station. Yeah. So I went to work for that company. It was sort of the natural move for a Canadian to go work there.
Gotcha. I'm curious what kind of led you to such a change from, I mean, you're still doing planetary space research, but you switched from robotics engineering to planetary geophysics, seemingly two completely different fields.
Yeah, they're pretty different. Like I said, I think robotics was appealing, but space is appealing on its own. And so after I'd worked at that company for a number of years, And there was also some other things happening. Like there was a project I was working on, which was really cool, and then it got canceled. And so I kind of went back to my old job, which was still cool, but I was starting to feel like I wasn't growing anymore. I didn't feel like that rapid growth phase of learning. Well, I felt like I was sort of passing that. Mm-hmm. And so I thought I should learn about some other things. And I was interested in maybe like space exploration missions where they're sending rovers to other planets. So that's what I did in Japan. I worked on rovers for planetary surface exploration. And at some point I thought, it's really interesting from the point of view of an engineer. You just want to build stuff because it's cool to build stuff. That's it, right? And I know that there's some sort of science questions that they're after, the scientists are after. I don't know what those science questions are, but I thought if I learn a little bit more about the science questions, then that would make me a really valuable engineer. I'd be like, still be an engineer, but I could also understand enough about the science that I could work with the scientists and be like a really valuable person on these space exploration missions across the solar system. Yeah. So that was when I kind of decided that when I was in Japan, I thought that's what I should do. And I thought I'd maybe end up working at JPL as an engineer, but I thought I better learn about science. And I ended up I realized you're not going to learn very much in like a 1 year, 2 year master's program. And so I thought, I guess I have to do a PhD in planetary science. Mm-hmm. So I thought I would start doing that and then eventually come back to engineering. But once I started the planetary science, I just was hooked. I just found it was a very different mindset. Like you said, the whole approach is different. The way you think about things is different. So it was a bit of an adjustment when I first got to grad school at Santa Cruz. But quickly, I really got into it, and I decided that that's actually the thing I want to do is more the science. And so now it's the other way around. I'm a scientist who also understands enough about the engineering that I could maybe have conversations with the engineers.
Gotcha. Yeah, that I can kind of connect that to an idea that I talked to with a guest on podcast. His name was Shabam Pandi. He's a data engineer and back-end developer. And he was talking about advice for students in computer science and things like that. And he said to try to understand what's under the hood, and that'll make you a lot more valuable.
Right.
And that just kind of flipped in my mind when you were talking about how you wanted to be more valuable as an engineer. So you took the time and effort to really learn about the problem that you were trying to address with the engineering. But yeah, it's funny and that you got so hooked on it and just kept with it. I'm curious how much friction you had going into a new field like that, especially when you're well established in another field already, and you, correct me if I'm wrong, kind of have to start from ground zero.
Totally.
Yeah.
There was friction for sure in a couple of ways. Like one was like, I didn't know what I was talking about. I had no background in geosciences or anything like that. I'd never even taken a course in courses that I ended up later teaching. I'd never even taken those courses. So I was kind of coming out of nowhere. And so as a student, like applying to grad school, I think, someone had to sort of take a chance on me. I'm kind of coming out of left field. And it happened that one of the places I was interested in going was Santa Cruz, University of California at Santa Cruz. And there was a professor there at the time who was super interested in missions. And so from his point of view, I was like this perfect person who also understands the engineering side. And so that was like a really good fit. And then, so he invited me to come there and that worked out well. I don't think he would have even wanted a student who was not interested in missions at all. And so that ended up being an asset. But I think a lot of people might have thought like, who is this guy? What is he? Where is he coming from? And then I wouldn't call it friction exactly, but I had a lot of stuff to learn when I first got there. So I was sort of taking some classes along with the undergraduates just to kind of catch up in certain areas that I, didn't have background in, and just basic earth science courses. Mm-hmm. And also there was a mindset shift that had to happen because as an engineer, especially working in like human spaceflight, it was International Space Station. I guess I didn't explain that, but that was my job, was in space robotics, was helping to build the International Space Station. That was a big part of it. And so when human spaceflight, you have to be very, very careful because like something goes wrong, people die. And so there's like so much red tape. Everything had to be super double checked. And there was lots of factors of safety margin and all this sort of stuff. And then I get to planetary science research and people are like pretty happy if they're within an order of magnitude of an answer. And it was very hard for me to accept that. I was like, what do you mean? Like, this is meaningless. We need to get down to the bottom of this. And they're like, no, that's pretty good. So it was like I was a little bit frustrated with that at the beginning, but then I came to see it as kind of liberating. We're just trying to get the shape of an answer to start with, and that's kind of empowering. Like you don't have to stop just because you don't have every single piece of data in hand yet. You can start somewhere and then figure it out as you go. What further measurements you want to make and so on.
I had that same exact thought process when I went into that, especially like taking classes through high school and learning that science should be so on the dot and so accurate, and kind of building up this idea of what science is in my head. And then I'll never forget, I gave, so Don Blankenship is a coworker of yours and my supervisor, just for the listeners for some context. So Don told me, or I gave Don an answer on some like temperature model that I made or whatever. And I'm like, yeah, but I really need to hammer down the uncertainties, blah, blah, blah. And he's like, I don't know, it's good for government work.
Yeah.
And it's a funny saying of his, but it really does relate to the idea of like, if you're within an order of magnitude of the answer on these huge systems, you can even though you're an order of magnitude you have an order of magnitude of uncertainty on your answer. The system is so huge that it's precise enough, and
it's a lot better than nothing.
Yeah, exactly.
And it's the starting point, and like you do get better over time. Like things that you had an order of magnitude guess at 20 or 30 years ago, maybe we have much better numbers now, but it's only because you were okay with starting with that coarse answer, and then that helped you guide your thinking in terms of, okay, how can we do this better? But it doesn't have to be like all done perfectly the first time. Yeah, that's a good probably thing in general and to think about in life. Like if you're stuck waiting for everything to be perfect, you're never going to do anything.
Yeah, that's a fantastic idea. I fully subscribe to that.
There's so many directions.
Man, it was on the tip of yeah. Here we go. So I'm curious about how sparse the data is in your field when you have to send out this satellite to Enceladus or Saturn or Jupiter or Europa, whatever, and it's taking 10 years to plan the whole project, and then another 10 years for it to get there, and then years to process everything and get it all back. So I can't imagine that there's a surplus of data in planetary geophysics, and I'm kind of curious how you guys work around that.
Yeah, that's a great question, and it kind of depends on what kind of measurement you're talking about and where. So there are places like in the outer solar system, like you say, the missions are very infrequent. It takes like 7 or 8 years to get out there, like to the Saturn system, say. And so you're not going to send a mission very often. And then there's a lot of waiting around when you do send a mission. And then again, it depends a little bit on the type of data. So one of the types of data that I work with is gravitational fields. And the gravitational field, when you're looking at a body like the Earth or the Moon, you can put an orbiter in, you can get very high resolution gravitational field data. But in the outer solar system, we're not going into orbiter on these little moons of Saturn. Instead, we're just doing a flyby once in a while. And all you do is track the trajectory of the spacecraft during that flyby. And it's somewhat influenced by the gravitational field of that moon, but only in the sort of plus or minus 60 seconds around closest approach. So it's a very brief window. And so you're not going to get a beautiful 3D model of the gravitational field. All you get is like very low order, very coarse, it's a handful of numbers. It's like summarized as like 2 or 3 or maybe 5 numbers. And that's all the information you get. So for example, for Enceladus, we have the gravitational field, the quadrupole gravitational field, and then one component of the octupole field. It doesn't matter what this means. The point is that in the quadrupole field, only 2 of the numbers are not 0. So there's only 3 numbers, a number called J2, a number called C22, and another one called J3. Again, it doesn't matter what those mean, but those are the 3 numbers we have, and that's all we're going to get until we go back to Enceladus, which is going to be in 30 years. Mm-hmm. So yeah, sometimes there's very little data to work with. But on the other hand, on a body like the Moon, you have pretty rich data sets sometimes. So we had the Grail spacecraft, which was a pair of spacecraft that were laser tracking to each other to measure how the gravitational field of the Moon influenced the movement of the spacecraft, and they use that to figure out what the gravitational field of the Moon is. And they've got very high resolution, something like degree 2000, which doesn't matter what that means. It's just like it's a huge number of numbers and you can't possibly understand them all. You have to make all kinds of models, and It's very rich, and people are still figuring that out. There's still data even from Apollo. So Apollo, you collected samples on the moon, and there were some measurements from orbiting spacecraft, and that is still being processed, 50 years later. So yeah, it really depends on the kind of measurements. Sometimes there's a wealth of data and Cassini orbited Saturn for 13 years and collected a lot of information. And so that's still being processed in some ways. So sometimes there's a lot, and then sometimes there's not very much, but it really depends on what kind of measurement and where you're looking.
Do you have to fill in a lot of the gaps with computer modeling and things like that?
Yeah. I'm trying to think about it in terms of filling in the gaps. I mean, certainly there's some literal gap filling, like interpolation between coarse measurements, but the type of measurement that I was describing, it's not so much that there's something in between, it's just that there's higher resolution information that you're never going to know.
Yeah, maybe I meant more metaphorical.
Yeah,
like
right.
Gaps, yeah.
I guess I'm trying to think of your question in all the different ways that what you could mean. But definitely, yeah. So what I do is, a lot of what I do involves computer modeling. It's part of what I do. So some of what I do involves taking some of the data, like say magnetic field data for the moon, and doing some processing with that, or optical data from optical images of the surface of the moon, and there's some processing steps involved there. And there's other kinds of data where I'm not really processing any data. I'm just like, how can I explain the data? And then for me, explaining the data mostly means making some kind of model of the physical processes that are happening, and then predicting what the measurements would be, and then eliminating the models that predict the wrong measurements. And so sometimes, even if there's only 2 or 3 numbers, that you work with what you have. And so then sometimes you're left with a lot of degeneracy in the models. A lot of possible different models will all produce the same kind of observations, or up to the point of the observations that we have. So that's something that you have to deal with sometimes. But you try to get your hands on as many different kinds of constraints as possible. Mm-hmm. And often the way they intersect across the parameter space, like if I make this measurement, it means that I'm not over here, it means I'm not over there. And if I make a different kind of measurement, it means, well, I'm not up there and I'm not down there. And so the intersection between those constraints allows me to get a pretty good constraint, even though each of the measurements separately is not all that tight. See what I mean?
Yeah, you explained that really beautifully, because I've done the same thing with polar geophysics, where you try to intersect the uncertainty that you have for, let's say, accumulation rate over time. So how much snow is falling on the top versus the surface temperature over time. So you have this window and that window, and exactly like you said, you find the intersection between the two, and then you try to get the string through the needle head.
Right.
Yeah. So can you give me a brief explanation as to why planetary bodies generate magnetic fields?
Yeah. So basically, if you have an electrically conductive material, whatever that is, if it conducts electricity and it's in motion, then you get this interesting interaction where the presence of any magnetic field, if you move an electrical conductor in a presence of a magnetic field, that generates currents in the conductor, right? And then when you have currents flowing through a conductor, that also generates a magnetic field around the current. And so you have this complex, if you have complex motion in the interior of a planet, like let's say the liquid metallic core of a rocky planet, and you have, say, convection and you have rotation, you have this very complicated motion. So there are magnetic fields induce currents, and then those currents induce more magnetic fields, and then it has to be a 3D geometry. Things have to be changing in 3 dimensions, and then that introduces more magnetic field, and it eventually amplifies up to the scale of a global scale field for a body like the Earth. Mm-hmm. It's always decaying away as well, so it has to be an ongoing regenerated process. So if those currents ever stopped, or if the convection slowed down or whatever, then it would eventually decay away in a relatively short period of time, like tens of thousands of years, I think. So not all bodies have magnetic fields, but a bunch of them do. So I kind of described it in terms of rocky planets. For giant planets, it's pretty different. So it's even in the case of Jupiter and Saturn, whether there's a rocky or metallic core is sort of unclear. Something probably higher density down there, but it's probably not as simple as just like a rocky interior. And in any case, it seems like the magnetic field is being generated elsewhere, like higher up in the hydrogen envelope. So at those pressures and temperatures, hydrogen is electrically conductive. And so it's in complex motion, it's electrically conductive. It's not what we normally think of as a metal, but it's basically metallic hydrogen in that state. And that allows it to conduct electricity, and then you can generate magnetic fields higher out. In the case of Jupiter and Saturn, there's still like pretty well organized magnetic fields, like on a global scale, that look dipolar, kind of like a bar magnet magnetic field for the whole planet, like Earth. But for bodies like Uranus and Neptune, it seems like the magnetic fields are much more complicated than that. So probably because they're not generated right in the center, they're probably generated further out and in some asymmetric ways. So you get these very complicated magnetic fields on those bodies. So that's not all that well understood yet, but that's just kind of, there's a range of different ways you can do it.
Yeah. Krista does a lot of research.
Krista Soderlund is an expert on that.
Yeah. So to better understand induction, so if I have like a bar magnet and I have a copper wire and I rub that copper wire on that bar magnet, I'm going to generate.
Yeah, they don't have to touch. They just have to be a movement.
Yeah, in the presence.
A changing magnetic field induces currents, yeah.
Yeah, I think a great example is having like a loop of wire and then you run a bar magnet through. Yeah. Like, and you move it up and down and oscillate it. That'll generate.
Or vice versa, have the magnet there and just move the wire around.
Yep, exactly.
Mm-hmm. Or just run current through the wire and that creates a magnetic field. Yeah.
So I want to go back to how a magnetic field is generated on Earth. So it's good to think about it as you have liquid metallic elements like iron and nickel and things like that in the outer core, and the heat from the inner core is acting like the stovetop, and it's heating up. So say you have a boiling pot of water, it's heating up that water, and then you have these three-dimensional currents over time, right?
I think of it like, yes, you end up with these three-dimensional convection currents in the core, in the outer core. It doesn't have to be the outer core, by the way. Even if there was no inner core, this would still work. So I think of the way I think of it is that you're pulling heat out because you're radiating heat out from the surface of the planet out to space. And so the surface of the planet ends up being quite cool, close to zero from this point of view. And the middle of the planet is something like the temperature of the surface of the sun. And that's just because it got so hot when the planet accreted. And now it's all that takes time for that heat to get out.
Accreted means like come together through gravity and.
Right. Yeah. Sorry. Yeah. When you form planets,
gotcha.
Generally you think about a bunch of stuff collecting together under self-gravitation until it all smashes together. And as it smashes together, all that stuff that was far apart, all that gravitational potential energy turns into kinetic energy. It all comes together and then heats everything up. And so planets end up starting out pretty hot. And they're just cooling. So the outside cools quickly. And then, especially if they're hot enough that they're totally molten, then the metals will segregate out towards the middle. And then you end up with this rocky mantle surrounding the metallic core. Never mind inner core yet. You just have a solid or a liquid metallic interior. And then this rocky stuff is also liquid initially, but it's going to conduct very vigorously if it's liquid. And it's going to cool off very quickly and solidify. And then you have this big blanket sitting on the top. So how much you're pulling heat out of the core is a function of the viscosity of the mantle, structure of the mantle, the thickness of the mantle, things like that. So coming back to your point, yes, it depends on how much heat you're pulling out of the core into the mantle. And if you're pulling the heat out faster than you can conduct it out, then the core is forced to convect. That liquid metallic core is forced to convect. If you pull it out gradually enough, then it will just be able to conduct. Like the fluid can be kind of thermally stably stratified so it's actually just conducting, even though it's a fluid.
Yeah.
Just like, I think your stove would be the same. If you go slowly enough, it'll just heat through like as if it's a solid rather than, right? But yeah, so if you're pulling the heat out too fast though, then it will start to create density anomalies because you suck the heat out of the things and that changes the thermal expansivity means that that stuff is going to shrink and it's going to be more dense and then it's going to sink. And so it's almost the opposite of like heating something from the bottom from a stove. It's actually cooling it from the top. Mm-hmm. But it's the same idea. Yeah. So whether there's a solid inner core there or not is sort of independent of this question of thermal convection. But there is, and maybe this is what you're thinking of, is why it's thought to be important that there's a solid inner core. Is that what you're thinking about?
Sure. Yeah.
Is that there's another way of driving convection, which is that once you start to cool at some point the temperature of the core gets below the melting temperature, then it will start to crystallize. And in the case of the Earth, because of the high pressures, it ends up crystallizing from the center outward. And so when you're crystallizing from the center, now what happens is as you're crystallizing, there's a preference for, so this fluid is, like you said, it's iron, but it's got some other lighter elements in it. And there's a preference for when you're crystallizing, for it to crystallize pure iron and reject light elements. So light elements end up partitioning preferentially into the fluid. And so you end up with this solid inner core that's pretty close to pure iron, and then the liquid outer core is getting enriched in lighter elements. And so that enrichment is happening at the boundary between the inner core and the outer core, the inner core boundary. And so as you're crystallizing, you're rejecting light elements, you're basically creating fluid there that's lower density than the rest of the fluid. And so that buoyantly rises up, and that drives convection from the bottom.
Oh, wow.
So that's kind of a long explanation, but there's sort of two main ways of driving convection in the Earth's core. Thermal convection, if you're pulling heat out faster than you can conduct it out, you have to convect thermally. And then compositional convection, if you're introducing light elements because you're crystallizing and you're preferentially rejecting light elements at that inner core boundary, then you introduce density anomalies that drive convection the other way.
Is that crystallization process something that tapers off over time as you develop a more and more pure iron core and all of those lighter elements kind of make their way to the top and stay there?
Yeah, that's a good question. So there's a few different opposing effects. So as your solid inner core is growing, as the surface area gets bigger, there's more and more area to react. And so it actually gets more and more vigorous initially. So the compositional convection starts out being zero before the inner core nucleates. And then once you nucleate an inner core, you start introducing these density anomalies, and it quickly gets stronger and stronger. But yes, it does slow down eventually. Partly though, that's the thing, just because as you're removing, you have to also keep removing heat energy to actually crystallize the core. And that gets harder and harder over time as the whole thing gets cooler and equilibrates thermally. So that slows down for that reason. And then I think what you're getting at is another separate reason, which is that as you're enriching the outer core in light elements, you're also changing its chemistry. And so you're changing the melting temperature of the core. And so it is possible that would be an additional reason that it would slow down. So yeah, I think that does slow down over time. I mean, it gets bigger over time, but it's like the curve, looks like this. Like, I'm not left-handed, but it's like zero, and then the inner core nucleates, and it goes like that. But it tails up.
Yeah, for anyone that's not watching the video, it looks like one of those like Egyptian swords where it starts off flat and then kind of turns into a logarithmic function that tapers off over time. Gotcha.
Yeah. So I don't know if that answers the question.
It does, yeah.
Okay.
Yeah. Can we take a break for 1 second? So where were we? Oh yeah, so if that density-driven convection tapers off over time, and then I would imagine that heat from accretion isn't infinite, right? You have a finite amount of heat, so as you lose it to space, and as you lose it to, I don't know, maybe some other processes that I'm unaware of, how do you know when, like the cutoff point between I'm generating a magnetic field because I have vigorous enough convection and I'm not generating a magnetic field?
Yeah, no, that's a good question. So you're right. The thermal convection gets weaker over time. So that one looks the other way. Maybe I shouldn't draw because maybe that's the wrong way to do it. But it's basically like a inverse, like a 1/x kind of curve where it just like starts out high when you have a big temperature difference between the core and the mantle. And then that just diminishes over time. I mean, I'm speaking in general terms here. Obviously, there's like different ways of setting this up. But generally, things are cooling down over time. And the temperature difference between the core and the mantle is reducing over time generally, and so the heat flow from the core to the mantle is reducing over time. So the thermal convection gets less and less vigorous, and then at some point the heat flow is so slow across the core mantle boundary that it's possible for even though it's a liquid, for that liquid metal to just conduct the heat, and at that point thermal convection stops. So that it's basically, there's a simple equation for that to answer your question, like, is this thing bigger than this number or not? And if it's below that number, then there's no thermal convection. The crystallization thing is, again, like it's zero before the core starts to crystallize. So before that, there's no compositional convection. And then once the core starts to crystallize, then you can start to have it. But the shape of that curve, it depends on some things. It's a bit complicated. And it's also, there's some weird kind of exotic possibilities. Like, well, I say exotic from the point of view of Earth, because we're used to the way Earth works just because that's where most of the research has been done. But when you start to look at smaller bodies like Mars, or especially anything smaller than that, the pressure at the center is not that high. And so although the temperature goes up as you go towards the center, the melting temperature doesn't climb as much. Maybe I should explain that. So in the case of the Earth, it might be weird to think about this. Like, how is it that the core is, as you go down from the surface, you go down through the rocky mantle, and then you get to the core mantle boundary, then you encounter liquid iron, and then you keep going down towards the center, and then it gets solid, even though the temperature is going up. Well, like, why would it be solid at a higher temperature? And it's because the pressure is so high that the melting temperature is going up even faster than the actual temperature. And so these two curves are crossing in such a way that the solid ends up being at the center, and then you have this liquid iron envelope around that. But that's not the case for smaller bodies, where the pressure is small enough that the melting temperature doesn't go up that steeply. And so you can actually have the curves oriented the other way around, so that the place where the two curves meet first is actually at the core mantle boundary, not at the center. What that means is that you start crystallizing not from the center, but from the top of the core. And that's something they call iron snow. So you start crystallizing at the top. It's still, the crystals are more dense than the rest of the fluid, so they sink. But then they could also remelt as it gets warmer, as they go down. They can remelt, and then they can drive convection that way. So that's a whole different mechanism. This iron snow driven convection. I don't understand it very well.
That's super cool.
It's a neat idea, though.
Never heard of that, but
yeah.
Iron snow.
Yeah, sounds cool, right?
Yeah. Did you have more to say? I'm sorry.
I'm not sure if I did, though, because I don't know. I don't feel like I can explain iron snow any better than that. But the point is, like, all these things can change over time as you're changing the temperatures of these, as the whole system's temperature is evolving, and then the chemistry is changing maybe a little bit. So how the thing evolves can be complicated. Yeah. Okay. Coming back to your question was, like, how do you know when there's convection or not? So thermal convection is more or less simple. Compositional convection depends if the temperature is cool enough to crystallize. So how do you know if this is happening in a planet? Well, okay. Actually, now I think about it, there's a slightly more complicated answer to that, which is that, yes, it's just comparing these two numbers, but that assumes you know what the actual value is on either side of that equation, and you don't. So one of the key terms in there is the thermal conductivity of iron, and the thermal conductivity at iron at the temperatures and pressures that are relevant for the Earth's core is very hard to measure. Like, how do you do that in the lab? Have like thousands of Kelvin and like hundreds of gigapascal. You can't do it, not easily. And so we don't actually know that number, and it's uncertain by a factor of a few. So I think people used to think there was a certain number, like 40 or 50 milliwatts watts per meter per Kelvin. And then that's been revised lately. Like, now people think it might be 3 times higher than that. And if it is, then that means that the core should be not, the heat that's coming out of the core is not enough to drive thermal convection. And so the core may be thermally stratified.
So what you're saying is that the ability of iron to conduct heat energy changes as a function of its temperature and pressure?
Right.
Okay. And what they found was that it was 3 times less conductive than they thought it was?
More conductive.
More
yeah.
conductive. Okay.
Yeah. Although it's still debated, I think, because it depends how you do the experiment, and it depends on some other assumptions. It's not my expertise, but it seems like that's an ongoing, area of research, and it matters a lot because it changes the number by a factor of 3, like how much heat flow out of the core is compatible with convection or not.
So that tells us how hot and for how long, that conduction value tells you how hot and for how long does the core stay, which then tells you, is there enough heat coming from it to drive convection? Hope I'm getting that right.
I mean, in broadly speaking, yeah, but I think like in detail, it might. I don't know how much detail you want to go into, but
As much as you want. Yeah.
no, it's just like, how do I think about it? So the one number is coming down over time. That is a function of how much heat is coming out of the core. And I'm thinking of this from a modeler's perspective, but that is something that declines over time generally. And then the number you're comparing that to has to do with how conductive that material is. And then that's just it's where those two curves cross. So in terms of the evolution point of view, like how much time the thing spends in this mode of where this convection is happening, I don't know how directly translatable it is to time. I think you have to basically model it.
Yeah.
Yeah.
You have to throw it in some kind of function that'll tell you.
Yeah. Function is a very complicated function. Yeah. Some kind of thing that tracks the thermal structure and how that structure changes over time as heat is being transported through the system.
So it's
a thermal evolution model.
Gotcha. So circling back to my original question, so Mars does not have a magnetic field, or if it does, it's very faint right now.
Yeah, I think there's no magnetic
field at all.
Apart from in the crust.
Okay.
There's rocks that are magnetized on the surface, but we can come back to that if you want. But
that'd be a great thing.
But there's no internally generated global magnetic field like on Earth.
Yeah.
Right.
So that is a consequence of Mars not being big enough, so you don't have enough pressure in the core to be able to drive convection in the way that we see it on Earth.
Yeah, I don't know if it's because of pressure, but yeah, I think you're right that it's partly because it's smaller. So like to a first approximation, you could think about how quickly, like I said, planets start out hot and then they cool off. And how quickly they cool off is kind of a function of their surface area, but how much heat energy they have in them is more a function of their volume. So the volume goes with the cube of the radius and the surface area goes with the square. And so that means that smaller bodies cool off much more quickly and bigger bodies cool more slowly, very basically. Yeah.
And that's
so Earth's radius is something like twice the radius of Mars. It's not exactly that, but it's close enough. So that means the surface area is like 4 times as much, but the volume is 8 times as much.
Yeah.
So it's going to take that much longer for heat to get out.
Oh, yeah. So
it's oversimplifying it, but you get the idea.
Yeah. Definitely like orders of magnitude longer. Is the time at which we run out of energy to generate a magnetic field is billions of years from now, right? On Earth?
Well, that's a good question.
Depending on the conductivity research and things like that, but our kind of general understanding right now.
Well, actually, no, it depends on, so like I said, there's these two processes. There's one where you're thermally convecting, which that is strong at early times and gets weaker over time. And then there's compositional convection, which is 0 initially, and then it starts to go up when you start crystallizing a core. So in the case of the Earth, we have a solid inner core. It's been crystallizing for some time. We don't know how long, but some models suggest it's something like the last 800 million years or maybe 1 billion years. And so that means that the magnetic field that existed on Earth, we know it existed on Earth all the way back to like 3.5 billion years ago or 3.8 billion years ago, something like that. It must have been powered by thermal convection early. But right now, it could be just compositional convection that's keeping it alive. So it could be, it could be that thermal convection is no longer happening in the Earth's core, and the only thing keeping the Earth's core generating a magnetic field is that there's compositional convection. And so there's no guarantee that thermal convection could go on for billions of years, or that a planet like Earth would have a magnetic field all the way till today, because look at Venus. Mm-hmm. So Venus is pretty similar in size to Earth, but it has no global magnetic field. So actually that's the proposal that I just submitted recently, is about this exact topic. It's like just basically understanding, why does Earth have a strong magnetic field and Venus doesn't? They're so similar. What accounts for the difference? Yeah. So it could be that Earth just dodged a bullet and could have had its magnetic field die. It could be that the thermal convection stopped, and then before the inner core started to grow. And in that case, you would have so that could be the situation on Venus. It could be that Venus had a magnetic field until very recently, say a few 100 million years ago. Thermal convection just recently stopped. This is all hypothetical. But there's no inner core yet, just because the core chemistry is such that we haven't reached the melting temperature yet. It hasn't cooled enough to start crystallizing. And it could start doing that, tomorrow. Start crystallizing tomorrow, and maybe, a few 100 million years from now, you have a magnetic field again on Venus. So it could be, it's sort of this like kind of a cusp. I think of it as like magnetic field strong in the beginning, goes down, may go below the threshold where it's not possible to drive convection, and then it could come back up in the future. And so it could be that Earth dodged a bullet and hit that cusp point before reaching the threshold, so that it always had a magnetic field. It might have gotten weak and then started to strengthen up again. It could also be the case for Mars. Like we don't know, but Mars probably had a magnetic field early in its history, but probably only for the first 500 million years or so, and then it shut off. But it could turn back on in the future. Like if the core is cooling enough to start crystallizing, it's possible that it will start to generate a magnetic field again in the future.
Yeah. That's I never thought of it like that, and I'm curious about. I mean, if Earth had a thermally driven magnetic field to start, and then it tapered off over time, I'm wondering if you could find evidence of that in rocks on Earth that have recorded the magnetic field.
Yep, that's a great question. So this is research by my colleague Peter Driscoll. He exactly the same reasoning that you just articulated. He said, well, it must have had a point where it was at a minimum before the inner core started to nucleate. So there should be, in theory, in the paleomagnetic record, there should be some evidence of like a minimum. But the problem is the data are very scattered around that time. And so they did a paper, and there's a bunch of numbers and they're kind of all over the place. So it's not enough to be a real smoking gun of that. But with maybe more samples, or I don't know, it's possible that there'll be future work that shows that.
Yeah, I mean, I would imagine if it's in the time frame or like post-Cambrian explosion, then
no, it's probably before that.
Probably before that. Yeah, because I was about to say you would probably have a huge extinction event. I can't imagine that would be a great day if your magnetic field went down by orders of magnitude or completely shut off. Get bombarded by radiation and things like that. But gotcha.
Although the Earth's magnetic field reverses every so often.
Yeah.
But we don't know what that looks like when it's doing that. So.
And is that reversal thermally driven or compositionally driven, or both? Maybe?
Oh no, it's sort of independent of this. It's more about the field structure. So I said you have to have convection and some complicated fluid motion in the outer core to support the magnetic field, or in the core, let's say. But that magnetic field may be very, very complex, and then maybe it gets organized in such a way that it looks like a dipole, looks like a bar magnet from the outside. But like deep inside, it's much more complicated and it's much more dynamic than that. And so, it might look like it sort of looks like a bar magnet for a while this way, but that's just the like macro scale. And if things just shift over just a little bit the other way, it could flip so that the result is that it looks like the bar magnet goes the other way. That's very complicated what's going on down in the core.
Is that?
And this is sort of an independent question. Like this, it's all of this requires the whole thing to be, having vigorous motion. Yeah.
So I'm trying to think of like the magnetic field reversal. Is that driven by a change in the actual like kinematic convection? So like I'm convecting in this direction to my left, and then all of a sudden you start convecting to the right, and then that creates a cascade. Or is it the actual like field, like magnetic field, electric field that's being generated is kind of morphing, or maybe both?
Yeah, I mean, I definitely didn't explain this well, and I don't think I will be able to explain it well, but I think what I'm saying is I don't think it's something like that. I don't think it's like a sudden change. I think what it is we're lucky it ever looks stable. It's like so chaotic that it's basically all over the place down there. But there's I think there's some, Gary Glatzmeyer showed me this one time, that there's some, you magnetize, once you have a solid inner core, you kind of magnetize the solid inner core, and that has a little bit more stability to it. So that sort of stabilizes things a little bit. And so that from the outside, it kind of looks quasi-stable, but it's just kind of barely hanging on. And then it prefers to be roughly aligned with the spin axis, but I don't think it cares very much whether it's this way or that way. And so it's just sort of like barely one or the other. But once it's on one side, it kind of stays there for a while. This is a horrible explanation, but like
no, I don't think it's bad. Yeah.
But yeah,
it's helping me understand a lot. And what about magnetic fields generated on the gas giants like Jupiter and Saturn? It's farther out in the kind of radius of the planet,
Right.
but would the same kind of general rules apply, and would you get like similar behavior of reversals and maybe thermal at first and then compositional later?
I'm not sure about the thermal and compositional. I have to think about that. I think it's pretty different. Some things are similar. So in the case of Jupiter and Saturn, their global magnetic fields are pretty much aligned with their spin axis. In the case of Jupiter, it's tilted about 10 degrees from the spin axis, which is about the same as on Earth.
Yeah.
But on Saturn, it's like almost perfectly aligned with the spin axis.
So it's that like
to
pencil
within-
that we put through the planet and then it spins around kind of.
Yeah,
that's the
yeah,
spin axis.
yeah. And so it's lined up with that perfectly or as within measurement error for Saturn. For Uranus and Neptune, first of all, we barely measured them because we just had one spacecraft fly by that went through those systems, and so there's not that much to go on. There's some other kind of less direct measurements, but it seems to be much more complicated fields. And so I don't know if anyone really understands how. I mean, you should ask Krista; she would know better than I do. But like,
I should get her on the show sometime.
You should,
Yeah.
but I think she even would tell you that I don't think they're all that well understood yet. It's kind of one of the motivations for sending a mission to Uranus or to Neptune or both, because we have such a poor understanding of how those bodies generate magnetic fields. And those are like one of the most common types of bodies in the solar system, like sort of ice giants or like super Earth kind of that sort of scale, 10 Earth masses, 15 Earth masses. Those are very common in the galaxy, and yet we know so little about them. So yeah, I don't think it's well known, actually, the answer to your question, what those magnetic field generating processes are like in those kinds of bodies.
That's going to be a really interesting development when we start to learn more about that.
Yeah.
That's
hopefully the next, like, it seems like that's the plan, is the next big flagship mission to the outer solar system is a mission to the Uranus system.
I'm curious if if the Ryman Reason mission that's launching
Europa Clipper.
There we go. Is that going to?
Well, there's Europa Clipper and there's JUICE, which is the European
Gotcha.
Jupiter Icy Moons Explorer or something like that.
Are either of those missions going to collect any data on Jupiter, or are they solely focused on those icy moons?
I'm not sure exactly what's in their plan. I think they're mainly focused on the moons, but there will definitely be some incidental data collection around the giant planets, I'm sure, opportunistically. But I don't know how much of that's built into their plan.
Yeah. That was just like a curiosity of mine that I had on the spot. As far as generating a magnetic field with non-metallic. Normally non-metallic elements.
Metallic hydrogen.
Yeah, metallic hydrogen. There you go. Are there other elements that you like model or observe that generate magnetic fields in the gas giants, or theoretically could?
Yeah, again, this is kind of way outside my expertise, but I think I don't model anything like that. But I mean, as long as it's electrically conductive, then it's it could participate in the generation of a magnetic field.
Gotcha.
But yeah, I don't know. In fact, in the ice giants, the Uranus and Neptune, it may not be hydrogen at all. It may be like methane or something like that.
And would you say that a magnetic field could turn back on again in the case of Venus? Does that also apply to Mars? Could Mars' magnetic field theoretically start churning again?
Yeah.
And that's because of the crystallization process? Right. Gotcha.
Yeah. So it's not going to turn back on because of thermal convection. That's probably done forever. But yeah, if the core starts crystallizing, or it's actually possible that the core has already started crystallizing, but it's just so small that it's not yet enough of an effect to generate a global field. Mm-hmm. But if it's crystallizing, or if it starts crystallizing at some point, it should eventually generate a magnetic field again.
Yeah. But that would be in hundreds of thousands or millions of years?
Yeah. So I like to joke that my prediction from that, I wrote a paper on this, and the prediction was that one of the motivations for the paper was like, we have InSight, which is a seismometer that's on Mars now. And we started writing this paper before the thing landed. And the idea was like, okay, well, if they detect the presence of a solid inner core, that would be an interesting thing. Like, how could we square that with the absence of a magnetic field today? Because once there's an inner core, you're, generating this compositional convection. Shouldn't that drive a dynamo? And one of the things that we discovered is that if there is a solid inner core, it's possible that it's not enough to generate a magnetic field or like an observable magnetic field yet. But if you do see a solid inner core, then we predict that the magnetic field will turn back on for sure sometime within the next billion years. And that's a great prediction because, like, come back in a billion years and tell me if I was wrong, Yeah.
I can imagine that's something you could do with a lot of planetary science
Yeah,
problems.
it's true. I mean, obviously we try to do better than that. But,
of course.
But occasionally there are, some predictions that'll take a while to falsify. That's like that for everything.
Gotcha. So there's no way that a magnetic field could be generated on some kind of human timescale to where, habitation on Mars would be easier.
Oh, I see what you're getting at.
Yeah.
Well, it's just that things change so slowly. So if there's nothing there now, like, to a planetary scientist, 100 million years is a short amount of time. But, if something changes, goes from zero to like a decent magnetic field in 100 million years, that's not very helpful for planning for astronauts living there or something like that. Yeah, we're going to have to not bank on that.
Yeah, for sure.
We're going to have to come up with other solutions. Yeah.
So was that seismometer that you mentioned, was that a long wavelength seismometer that tried to get a picture of the chemical composition and kind of state of matter of the different stratigraphy?
The interior of Mars.
Yeah, interior of Mars. There we go.
Yeah, so they're trying to understand the interior of Mars. Now, it's not like on Earth where you have like tons of earthquakes all the time and you have thousands of seismic stations all over. You can get a very detailed picture of there's lots of sources of seismic energy and lots of stations to measure it at, so you can get a very good picture of the interior structure. This is baby steps. This is the first one, just one single seismic station and no active sources. So there's no and there was basically had to just wait for Mars quakes. And unfortunately, there weren't as many as they had hoped there would be. There were still some, and they got a lot out of that mission. So they did get a bunch of, Mars quakes that passed seismic energy through the interior of Mars and was received at that station. And so they were able to learn a bunch about the interior of Mars, but it's the beginning. So it's not like enough to get a rich picture like we have of the interior of the Earth.
Gotcha. So,
and also and maybe this is getting to your question.
Yeah.
Most of the source was from not too far away, from I don't know how many degrees away from the source, but it wasn't from the opposite side of the planet. There was very little from the opposite side of the planet or near opposite side of the planet. So it was hard to get seismic waves that went through the core. I'm not sure if they had any or how many there were, but that would have been the minority, I think.
Is that something they want to mitigate if they are to do something like that again, where they would consider the fact that they didn't get a lot of seismic waves from the opposite side of the planet, so they would put their instrument in a different location on Mars? And
yeah, I think if you were going to go back, you probably would be in a different location for a number of reasons. But the more you end up measuring from different places, the better. But also, it's also a question of the sources, and you sort of have to work with what you have on Mars in terms of sources.
So,
but yeah, it's possible that that one source that they found that was this one region that was active in producing most of their signal, if you went farther away from that, then maybe some of that seismic waves from that source would pass through the core. This is not my expertise. I should be noting, but yeah.
So, are we able to conclude the state of matter of Mars's core, or?
We know a few things about it. So we have some idea of the moment of inertia. So some idea of the radial density structure. We have some idea of the core is probably liquid metal, liquid iron, like on Earth, but probably with some probably more light elements like sulfur and silicon, things like that. There's a bunch of different arguments that I don't think I could reproduce here easily, but for why they think there's a lot of sulfur in the core of Mars, something to do with the density, and also just there are geochemical arguments for this. But it's not super well determined, I don't think.
Gotcha. And on the subject of Mars, I do know that you've done some research into Martian oceans, and when, maybe not oceans themselves, but when there was / could have been water on Mars, and what evidence we have for that. Could you talk a little bit about that?
Yeah, so it's not really my research. A colleague of mine, I think you're thinking of this paper I wrote with, it was Robert Citrin. He's the one who wrote the paper.
Yeah, I think that's the one.
And so I helped out a little bit with that. But I can explain a little bit about. So if you look at the surface of Mars, the dominant thing that you notice is that there's the southern highlands, which are these very high-standing, rough topography. And then there's the northern lowlands, which is this very smooth, topographically lower region. So they call that the crustal dichotomy on Mars, like the biggest feature that needs to be explained on Mars. And so a common explanation is that whole northern hemisphere was once an ocean. So that's like a seafloor, and it's just got very different morphological characteristics. And then there's a few different kinds of evidence for this, but one of them has to do with shorelines. So there are things that look like paleo shorelines in a couple of different places, and it suggests that there was an ocean, but the size of the ocean changed over time. So there was at one time like a large amount of water covering, say, almost the hemisphere, and then later there's shorelines that formed later that suggest that the ocean had later shrunk, and then now a new shoreline formed around this smaller ocean. That's a starting point. I don't know where you want to go from there with this.
Yeah, where does all that water go?
I think that's a good question.
Yeah.
I mean, I think it escapes. Like, I think it evaporates because your pressure is too low and your climate conditions are not right to support liquid water or enough liquid water on the surface, and it evaporates. And then it doesn't stay around because you have solar wind interacting with this is not my expertise, I should say as well, but like, you don't have a magnetic field protecting Mars from the solar wind, and so you have solar wind interacting with the atmosphere, and it's just easy for volatile things like water to go away.
Gotcha.
Out into the solar system.
Wow, so just evaporated up and then blown away by the leaf blower that is the sun.
Yeah, maybe, but take that with a grain of salt, because I said, this is not my expertise, so
Gotcha.
Exactly what all the processes that are involved I'm not really sure. Yeah.
So a little more of your expertise is the tiger stripes on Enceladus, right?
Yeah, I mean, again, that was a little bit of I like to dabble in a few different areas.
Uh-huh.
Yes, I did write a paper on the tiger stripes of Enceladus. Yeah.
So could you give, for the audience, just a brief explanation of what these tiger stripes are and kind of how they're formed?
Yeah. So first of all, Enceladus is a tiny moon of Saturn. It's about 500 kilometers across. But I would say it's arguably one of the most interesting places in the solar system because it is, even though it's tiny, it's extremely geologically active, which is very surprising. So it's the brightest object in the solar system.
Oh, wow.
And we knew this from the Voyager flyby that it had a very young-looking surface. There's like very few craters. A lot of old moons sitting out there, just nothing but craters. That's all that happens to them is they get hit by stuff. But this thing has a very young surface, vast regions of the surface where there's no craters, and there's these tectonic features suggesting that there's been some kind of geologic activity, some modification of the surface. So if it's geologically young, what is going on? How is this tiny thing active? And then when we got there with the Cassini mission, you could see, well, I think even with Voyager, you could see these tiger stripes. So this, notably at the South Pole, there's this series of fractures. Actually, I'm not sure if they saw them in Voyager or not, but certainly with Cassini, we have like imagery of these, there's kind of fractures all over the place, but there's this very prominent set of 4, or depending on how you count, maybe 5 fractures at the South Pole of Enceladus. And what's more is that with Cassini, you started seeing not only evidence of this thing being young, but actually being active right now. So there's water spraying out of these fractures right now. Like about 200 kilograms per second worth of water ice is coming out of these fractures.
Sheesh. Yeah.
And it just, some of it goes into orbit around Saturn. A lot of it just ballistically falls back down onto the surface of Enceladus. And that's why it's so bright, because it's essentially covered in its own fresh coating of snow.
Gotcha.
Yeah. And so with Cassini, we have a bunch of different kinds of measurements of this. There were disturbances in the magnetic field. There was a few other different things. But you could actually see with imagery, once they had the flyby geometry right, you could image it so that they were backlit by the sun, and you can actually just see these plumes of erupting material coming out.
Wow.
Yeah. And then later they organized some of the flybys so that the Cassini spacecraft actually flew through the plume of erupting material and sampled it with a couple of different instruments. They had a new ion and neutral mass spectrometer, and they had another thing called a cosmic dust analyzer, and both those were able to take samples. And so we know a bit about what those things are.
Instruments that take a physical sample,
right,
and then through some fancy geochemical process or just like chemical process in a machine, tell you the concentrations of different elements.
Yeah, basically. Okay. So they weren't designed for that. They were designed to pick up stuff that's in the space environment, but they never expected that there was going to be this high density spray stuff spraying out of a moon. But let's go see what it tastes like. And anyway, so we know that it's water ice. We know that it's rich in all kinds of salts, and we know there's organic molecules there. We know even large complex organic molecules. We just don't know what they are, because they get smashed up in the detector. So you don't know what, basically you can count the mass and you can figure out that it was a large complex organic molecule, but you don't know if it was alive or not. So maybe with a future mission, you could go back with a different combination of instruments that are designed differently and actually figure out whether that material is biological or not. Right now, we know it's interesting, but we don't know whether or not it's biological.
So through that mass spectrometer, you know how much carbon, how much nitrogen, how much oxygen, so you can guess which compounds this could be, but you don't know the actual arrangement of.
Yeah, I think that's right. Yeah.
That. Okay.
Again, that's not my expertise, but I think that's right. Yeah.
Okay, gotcha.
Yeah.
So, from my understanding, these tiger stripes are caused by.
Oh yeah, I didn't explain that yet.
You're all good. Now's your chance.
Okay, shall I?
So the eccentric orbit of Enceladus, right?
Yeah.
Yeah.
Well, okay. So first of all, we don't know how the tiger stripes are formed, but I can tell you some theories, including one theory that I suggested. Yeah. So first of all, I should explain what you're talking about with the eccentric orbit. So how do you put any energy inside this body in the first place? And the only way you can really do it is it's so small that there's no source of energy inside. There's not enough radioactive elements to keep it warm inside. So the only way that you're keeping it warm inside is through something called tidal heating, and that occurs because, like you said, the orbit is eccentric. So sometimes it's closer to Saturn, sometimes it's a little bit further away. I mean, there's a closest point in the orbit and a furthest point in the orbit. It's this elliptical orbit. And so that means that the tidal forces, which is the gradient and the gravitational force from Saturn, is stretching the body out, and then it's stretching and relaxing and stretching and relaxing. And so if you're stretching and relaxing something, if you do that with metal, it gets warm and soft, right? And so it's the same with ice. If you get the right sort of time scale and the right temperature, the ice behaves viscoelastically on that same time scale as the orbit. And so that means you are straining it. And so there's some basically friction inside the system, and that's heating it up.
So viscoelastically, kind of the same way an aluminum can would behave, where you kind of bend and but it's more almost like viscous, more almost like a liquid, right?
Yeah, it's somewhere in between. If it was purely liquid, it wouldn't do this, and if it was purely elastic, where it completely recovered all the energy, then it wouldn't do this. But if it's somewhere in between, then there will be strains that actually dissipate energy. Okay. And so essentially, what you're doing is transferring energy through the gravitational interaction between Saturn and the Moon. This is true of all pairs of bodies in the solar system. You're transferring energy between them, and in general, it's energy that's coming out of the rotation of Saturn. It's basically taking some of its rotational energy, but don't worry, there's plenty, and depositing it inside the moons of Saturn, and they're dissipating energy and turning it into heat. And so that's keeping it warm inside.
So rotational energy being the spin of Saturn? Or
you're slowing down the rotation rate of Saturn.
Oh, wow.
Yeah. It's the same as the Earth and the Moon interaction, right?
Yeah.
So the Moon is getting further and further away from the Earth, and the Earth's rotation rate is slowing. And that's what's happening. Is you're taking rotational energy from the Earth and you're putting it into the orbit of the moon. Actually, that's a slightly different thing, but but they're sort of related.
Or and then the moon is putting energy into the Earth through stretching and straining, and the Earth the same way, right?
It's also doing that, but yeah, it's not in terms of the orbital evolution. What's happening is the angular momentum from the Earth is being transferred into the moon, and so. But yeah, you're right that there's also interactions that cause, like for example, the tides, and then that gets dissipated. The ocean tides, because the land and the water respond differently. You end up with all this friction and waves smashing into things, and so there's a bunch of energy dissipated that way on the Earth. Yeah.
Okay. Yeah. Okay, so back. Sorry.
Yeah. No,
Put you on a
this
tangent.
is going to happen all the time.
Back to Enceladus.
Yeah. So I still didn't explain the tiger stripes at all. So we don't know how they form, but one idea that a colleague of mine had a number of years ago was that if there's some period in the history of Enceladus where it's freezing, like there's net freezing of the ocean, what happens is as you're freezing, the ice takes up more space than water. So basically there's a volume change there. And so now you're squeezing the ocean and you're putting the overlying ice shell into tension. And so as you gradually thicken the ice shell and freeze the ocean, you basically build up stresses in the ice shell. And at some point you will reach the failure threshold where the ice shell will crack. Now that gives you one fracture, but that doesn't give you and also why it should be at the South Pole or why it should be at one of the poles.
That's another question I was going to ask.
Yeah. This paper tries to answer all these questions at once. But one idea is that because of this tidal heating, I didn't explain this, but the tidal heating where the friction is happening at the bottom of the ice shell, that is maximum at the poles, and it's not obvious why, but it's just like a geometric effect that's where the maximum strains occur. And so that means that the place where the tidal heating is maximum is at the poles and it's minimum at the equator. And so that means that the ice shell is going to be thinner at the poles and thicker at the equator. So if you're building up stresses through this freezing, then at some point it's going to fail. And where is it going to fail? It's going to fail where the ice shell is thinnest, because that's where the stresses are going to concentrate. And so it's going to fail at one of the poles. And I think it's a 50-50 chance whether it's the North Pole or the South Pole. But once it happens, then that overpressure on the ocean is relieved. And so that mechanism is done. That is no longer available. You just made a fracture at one of the poles. In this case, it turns out to be the South Pole. That still doesn't explain why you get the rest of the fractures. So then the additional idea with that paper was that once you're erupting, once you make that fracture, now what happens is water fills up that crack to the level of neutral buoyancy. And at the top of it, it's exposed to the vacuum of space. So now that water is just boiling off. And there's people who have done research on that, like how do you keep it in a controlled state so that it's, there's enough back pressure to kind of stabilize the system so it doesn't just like freeze over. But you can have a steady ongoing eruptions for a long period of time. But all that stuff, some of it goes into orbit around Saturn, but most of it, like I said, ballistically just comes back down onto the surface. It snows back down onto the surface. And preferentially, that erupting material piles up on the flanks of that newly opened fissure. So if you can imagine, you have this elastic plate, now it's broken, and now you're piling stuff up on the edge of this elastic plate. And so that's causing bending. And so this is the idea of that paper, was that this is going to create bending stresses in that elastic crust, that ice shell. And at some point, and it turns out for very reasonable assumptions about the elastic properties of the ice shell, the maximum bending stresses occur 35 kilometers away, which is the spacing between the tiger stripes. So this is a way of explaining why so the questions, to come back to summarize them, like how do the tiger stripes form? Why are they only at one pole? Why are they 35 kilometers apart? Why are they in parallel sets? And why don't you see them anywhere else in the solar system? So I've explained some of those things now. So the first one, you get from this ocean overpressure maybe. But once you do that, now you start creating bending stresses, and that's why you get one fracture right through the South Pole, that's Baghdad, and then you get a symmetric pair, 35 kilometers out on either side of that, are Damascus and Cairo, the names of these things. And then once they erupt, or once they open up, then stuff starts erupting out of them, and then the same thing happens. Now they build up a load on the end of that now broken plate, and then they create another set of fractures and so on. So you get this kind of cascading series of fractures away from the pole.
Do the fractures decrease in size as you move outward from your progenitor?
A little bit. But another question is, they also stop at some point. So why do they stop? So, it could be that at some point you get far enough away from the pole that the background ice shell thickness is too big for the fractures to get all the way through. Maybe as the erupting material gets spread out over more and more open fractures, it's just not building up fast enough for it to kind of build up those loads before it can just relax away. So I don't know exactly why or how it stops, but those are a couple of ideas. But I didn't explain why it's only Enceladus, and that's actually the most interesting part.
Yeah. Why is it not Europa or other icy moons?
Yeah. So what I've told you is that I'm creating bending stresses, but what happens is when the fracture starts is now the bending stresses have to concentrate in the remaining unbroken part of the ice shell. And so as the crack propagates, the bending stresses at the crack tip increase as you go. But at the same time, you have overburden pressure. As you go deeper and deeper, into the Earth or into any planet, there's more and more pressure. The weight of all the rock or ice is squeezing you more and more. And so those two things are working against each other. But on Enceladus, the gravity is so small that overburden pressure is essentially irrelevant. So the crack tip stress just rapidly increases. So the crack just rockets all the way through the ice shell. Whereas if you go to like Ganymede or Titan or Callisto, one of those bigger ones, you could in theory have the same kind of mechanism where the bending stress starts a crack, but as soon as the crack propagates a little ways down, the overburden pressure stops it. So it just stops and it never gets going. And even if you could eventually keep building up the loads and propagate it little by little, eventually you get to the ductile part of the ice where the ice is warm and soft, and this is not going to work anymore. So you have to do it quickly on the time scale when the ice shell is behaving elastically, and that only works on small bodies like Enceladus.
Wow. So that icy crust is thin enough to where you can have that brittle kind of like cracking open, whereas because your pressure conditions are such, because it's smaller than these larger icy moons that have that kind of brittle ductile transition.
Yeah, I mean, it's mostly just because the gravity is bigger on. So it's kind of a function of the shell thickness and then the gravity. So gravity is so big on those bodies that the overburden, the pressure increases so quickly that it's going to stop the crack from propagating. Whereas on Enceladus, it doesn't.
So why is there so much pressure to where the water on Enceladus like bursts and spews out of these tiger stripes?
Yeah, so I don't think you need pressure to do that. It could be that it's just like I was saying, once you open the fracture and you're exposing the water to the vacuum, it's going to boil off just into the vacuum. Mm-hmm. So it's this concept of a controlled boiling that's sustaining these eruptions. It's not that there's pressure squeezing the ocean anymore. That's the idea for the first fracture, like how you make the first fracture. But once you do that, that overpressure is gone. Mm-hmm. And so you don't need overpressure anymore to keep those eruptions going. And
boiling, so is it hot at the surface, or is there...
No, boiling just because there's no atmosphere. So the pressure is, so like if you...
There's no, like in a container, there's gas on top of that water in that container, so that those liquid molecules don't evaporate off.
Yeah, like if I have a cup of water here, even if I don't change the temperature, if I lower the pressure enough, it will boil.
Gotcha.
Right. Yeah. It's like the water boils at a lower temperature in the mountains. Mm-hmm. It's lower pressure.
Gotcha.
Yeah. The phase diagram for water is kind of complicated, but pressure is important. Mm-hmm. So if you lower the pressure enough,
Gotcha. And so because I remember reading somewhere that Europa has kind of geysers spewing out, but I can't imagine to the scale of the tiger stripe. Is it the same mechanisms going on there, just smaller scale?
The observations are pretty limited. They're from, I think, the Hubble Space Telescope. Mm-hmm. So it's not from close-up observations, but there's a couple of detections of what looks like eruptions of some kind of water from Europa. Mm-hmm. When we go back there with Europa Clipper, hopefully we'll see some of that evidence. It doesn't seem to be anything like as intense as Enceladus. It's not like Enceladus is continuously erupting. There's some modulation in it, but it's basically continuously erupting for the whole, ever since we started watching it in like 2005. So Europa seems to be maybe less active, but it might be somewhat active. Maybe it's enough that once we're there watching it for a while, we'll see something. But I don't know. So whether it's the same mechanism or not, It's hard to say.
So in these icy moons,
We don't even know what the mechanism is on Enceladus, really. I mean, I told you some ideas, but we don't really know. Yeah.
So on these icy moons, are we? How much knowledge do we have of the internal structure, as far as like, is there some kind of like, so you have that icy crust, and then you have this layer of ocean, and then under that layer of ocean, is there like another kind of more solid rocky crust, or does it kind of, is there more of like a direct like mantle or core interface between that ocean?
Yeah. So first of all, I guess I should say, how do we know anything about the interior structure anyway? So we know something about the shape, and we know what the gravitational field looks like, and we know how those things are related to the rotation and the radial density structure. And so you can rule out certain radial density structures. You get some idea of how much there's rock and how much there's like water, whether it's frozen or liquid. It's hard to tell how much of it's frozen, how much of it is liquid, just from the density structure, because the difference between the density of ice and water is pretty small. But yeah, we know that it's Enceladus, something like 60 kilometer ice and water hydrosphere, let's say. And then underneath that is a rocky core. So the radius of that's maybe 195 kilometers, plus or minus a few kilometers. That's from the shape and the gravitational field. We can figure that out. But we use other things like the libration amplitude, which is something, that's a weird word, but it's like, it's basically how much it wobbles. So the way the ice shell wobbles tells you that it's decoupled from the rocky interior. Otherwise, it wouldn't be able to wobble that much. It would be more limited.
Oh, wow.
But so it wobbles around,
yeah.
And it wobbles so much that we think it's decoupled, meaning that there's a global liquid water ocean there. And then also the magnitude of the wobbling tells you how thick the ice shell is. So the combination of all those measurements gives us a picture of the internal structure. But as to what the seafloor looks like I don't think we have a good way of constraining that at this point. Like and it also depends what you mean by by crust. Yeah, we basically assume there's some kind of rocky core. We don't distinguish between like whether there's a chemically distinct layer where there's like rock of a certain type and then it changes to a different type. We don't really have the kind of resolution to be able to make those kinds of inferences at this point.
Yeah, I'm wondering how you would even make an inference like that, because you use, I guess seismics.
Maybe seismically.
Yeah. Because radar would go through the ice, but then as soon as you hit the water, it would all reflect, or almost all of it would reflect back up. And even seismic, like I'd imagine through an ocean as deep as that, it's going to be hard to carry a wave all the way through and then interpret that, or interpret what it traveled through before it went through that ocean.
Yeah, I don't know how far they've gotten, but there's certainly people thinking about that, like what we could do with seismometers on these kinds of bodies. But yeah, if you have an ice shell decoupled from the deeper interior, what your seismic imaging looks like, I'm sure they could do something.
Yeah.
But right now we don't know.
Yeah. And is Enceladus, through the kind of eruption in those tiger stripes, is it losing any significant amount of mass?
Yeah, you can do the math. It's like 200 kilograms per second is erupting, and then like 10% of that escapes into orbit around Saturn. That's what the E ring is. If you ever look at the rings of Saturn, there's these like pretty solid looking rings. They're all just like balls of ice. But then there's this diffuse looking one that's called the E ring. That's where Enceladus is, and so it's actually the guts of Enceladus that are coming out and making the E ring.
Oh, so it's making like a smoke trail as it goes around.
Yeah, but it's kind of like permanently there. It's kind of permanently there. And I guess there's some diffusion of that out into wider space. So I'm not sure how much mass loss there is from the system, but if you assume it's like the whole 20 kilograms per second that escapes Enceladus itself is all gone and never comes back to Enceladus, then you can figure out how long it would take to lose a significant fraction of its mass. I've done this before. It's like, it's not nothing, but it might lose like 1% of its mass over the history of the solar system or something.
Oh, wow. Okay. So it's nothing.
Well, that's a lot. It's a lot. 1% is a lot.
Yeah.
And like, don't quote me on that. Like, I mean, do you want to do the math right now? We could do it if you want.
Sure.
It's
so
like
20 kilograms per second.
Yeah. And so like in a year, there's like pi times 10 to the 7 seconds.
Yeah.
Roughly.
seconds, so that times 20 kilograms
Yeah.
in a year, and then how many years?
So then just do a billion years, go like 10 to the 9 years or something.
10 to the 9 years.
Yeah. So what is that?
So
10
that's,
to the,
you add the exponents, right?
yeah.
So pi times 20 is around 60-ish.
So you got 10 to the 17,
So
10
around
to the
60.
18. So something like 10 to the 18 kilograms in a billion years. Is that right? Is that what you got?
10 to
Did I do that wrong? 7, 8.
I think it would be 10 to the 60 times 10 to the 16th.
Okay.
Is that? Don't quote us on the math.
Yeah, I mean, okay. Well, we're getting hung up on that, but like,
Yeah.
it's 10 to the 16, 10 to the 17, 10 to the, yeah, anyway, whatever. 10 to the 18.
Okay.
And then the mass of Enceladus is about 10 to the 20. So yeah, it's like 1 times 10 to the 20. So it's about 1% of the mass in a billion years.
And even,
so that's a lot.
yeah, even,
But
a
it might
change
not
in
have been
that.
doing that the whole time. Like
Uh-huh.
maybe right now there's more erupting than usual, or I don't know. It's a good question.
And even a 1% change could influence the way it orbits around Saturn and things like that, right?
I think what matters is more the mass of Saturn, less the mass of the thing that's orbiting it.
Yeah.
But my first thought is like, it would, I don't know what it would happen if you reduce the mass by 1%, how much contraction there would be and what that would do to the ice shell.
Oh, yeah.
There should be, but I mean, it is an active ice shell, so it could have been resurfaced in the last, 100 million years anyway. So yeah, I don't know. Yeah. Maybe we did that wrong, but I think I've done that calculation before and it's something like that. So it's not nothing, but it's, yeah, I don't know. It's worth thinking more about.
Gotcha. And what was intriguing to me, and I want to make sure I'm understanding this correctly, is that there's I'm thinking of it like a Enceladus or Europa, these moons with these icy shells around an ocean. I'm thinking about them as like an egg, and the actual egg shell is kind of wobbling while the inside part of the egg is moving at its own independent direction and speed and whatnot.
Yeah.
Is that an accurate way to think about it?
I think that's somewhat true. Yeah.
Yeah.
I think that the spin state of the liquid part of the core could be distinct from the rotation state of the rocky mantle that's surrounding it. Yeah.
Yeah. And is it, does that also happen on Earth? Like the speed at which the outer core and the outer core spins is different from.
Yeah, I think that's
the
right.
mantle
I don't
and
know the numbers or
crust.
anything like
Yeah,
that, but
yeah.
I think that's right.
Gotcha.
I think it's not just that they spin at they might spin at different rates, but they also might spin about a different axis slightly. But yeah, I'm not an expert on that, but I think that's right. Yeah.
Gotcha. And why does Enceladus's water ice that's erupted out and that does escape into space, and even the water ice that doesn't, there's no magnetic field. I mean, there's the magnetic field from Saturn, which may be your answer to this question, but there's no magnetic field generated on Enceladus, right? So the water that you're spewing out has no, at least from Enceladus, has no defense against solar radiation and things like that. And it seems like that happened on Mars, where there was no magnetic field. So when you evaporate this water into the atmosphere, it kind of gets blown away. Why is the water being erupted out of Enceladus not blown away?
Yeah, maybe it is. Yeah.
Maybe it is. Okay. So has anyone looked into like how much mass that's escaping Enceladus is actually working its way into that E-ring around Saturn?
Oh, I see. Yeah.
Yeah.
People have modeled that. Yeah. I'm not intimately familiar with the details, but people have modeled it in like pretty compelling ways. They show that the geometry looks right, like close-up images of Enceladus embedded in the E-ring creates these interesting kind of streaming features of the stuff coming out and then ending up in the E-ring, and it matches models. So that means that to me indicates that people have a somewhat good handle on that problem, but in terms of like what they're assuming in terms of how much of the mass is retained in the E-ring, I don't know.
Gotcha. And then lunar swirls.
Okay, big jump.
Here we go. Big jump. But I wanna talk to you about them before we head out of here.
Sure.
Again, like the tiger stripes and like magnetic fields and things like that, could you give a brief description of lunar swirls and how they form and things like that?
Yeah. So lunar swirls are these very strange looking optical markings on the surface of the moon. You should Google them to look at them. They're pretty, but they're very strange looking. They're like these alternating series of bright and dark markings, these kind of blotchy patches of white stuff on an otherwise dark background is what they tend to look like. And they're unique. You don't see anything like them anywhere else in the solar system. And they were known. You could see them with telescopes from the Earth. And but after Apollo 15 and 16 in particular, they left these sub-satellites in orbit. After the astronauts returned to Earth, they left these little sub-satellites that orbited for a few months and had magnetometers, and they collected data. And they found out that these things are co-located with crustal magnetic anomalies. So they're these weird-looking optical features, and they're all co-located with crustal magnetic anomalies. So what we think is happening is that these are places where the strong crustal magnetic anomaly is interfering with the way the solar wind plasma is accessing the surface. And so solar wind is a stream of charged particles coming from the sun. Mm-hmm. And when you move a charged particle in the presence of a magnetic field, the Lorentz force deflects those electrons or those ions. And so normally the surface of the moon would just be so there's no atmosphere. So you get, let's get into the concept of space weathering. So space weathering is what happens to airless bodies that are exposed to the space environment. So if you have an atmosphere like Earth, then all the stuff is, the solar wind is first of all organized by the magnetosphere and funneled into the magnetic poles, and that's what gives you the aurora. But you also have micrometeoroids, so just small things that just hit the atmosphere and burn up, and they give you a shooting star. But when you don't have an atmosphere and you don't have a magnetosphere, all that stuff just rains down on the surface. So an airless body like the moon just sees everything hitting the surface, all the way down to the tiniest scale. So you have large impactors that make big craters, but you also have tiny, tiny impactors, like even an individual proton or something that small hits the surface and makes like a crater on the tiny, tiny scales. And that has the effect of altering the optical properties. We can get into that if you want, how it does it. But what happens is if your solar wind, which is a component of this space weathering, is being magnetically deflected by the presence of a magnetic field, that means it's going to access the surface in a different way. And so whereas like a normally exposed surface would just kind of have this uniform exposure to solar wind, swirls are places where the solar wind access is all complicated, and that's what we think is making those structures.
So it's following, like those charged particles are following the field lines.
Exactly.
Of that some kind of magnetic body under the surface.
Right.
Gotcha. And how big are these lunar swirls roughly?
So they're organized they're just kind of in a few patchy places all over the moon. But some of them are complexes of hundreds of kilometers across, but they're all consist of like small scale features. Like the transition between the bright part of the swirl and the dark part of the swirl is never more than a few kilometers, so maybe 5 kilometers. But they're also all the way down to like maybe less, like hundreds of meters, all the way up to maybe 5 kilometers. Mm-hmm. But even though there'll be clusters of them that are hundreds of kilometers across, there's always some like short length scales in those features.
Gotcha. And I'm thinking about the origins of lunar swirls and why you have a magnetic body just sitting under the surface.
Yeah, it's a great question.
I'm thinking maybe some kind of impactor comes down and it's full of some kind of magnetized metal or element, and then kind of gets buried over the surface, but its magnetic field is still present. Is that?
Yeah, it could be that, or it doesn't even have to be magnetic. It could just be a metal-rich impactor, and it like spills its guts on the moon, and it's hot because it's just hit all that kinetic energy has heated it up when it hit the moon, and so maybe it's just hot blobs of metal, not magnetized. But if you have a magnetic field, so the moon doesn't have a magnetic field today, but like Mars, it looks like there's evidence that it did have a magnetic field early in its history. So if this happens at a time when the magnetic field is present, then those things, like if you cool a rock down, especially if it's rich in certain kinds of minerals, metals and like magnetite and things like that, if you cool that down in the presence of a magnetic field, it records the ambient field. And so it becomes permanently magnetized. Any permanently magnetized rock that you find on the Earth is usually magnetized in that way. Mm-hmm. It's thermal remnant magnetization.
Yeah, that's how they, I don't want to say proved, but that was a large piece of evidence for plate tectonics.
Yeah, that's right.
And it's what we were talking about earlier, where when you have that taper off from a thermally driven magnetic field to a compositionally driven, you would see some kind of record of that exactly through the process that you're talking about.
Right.
Yeah. So, what does the overall shape of the lunar swirl tell you about the kind of body that's underneath it generating that magnetic field? Like if it's long and strung out, is that body also long and strung out? And if it's kind of all concentrated at one point, does that reflect the body as well?
I think that's right. I think that's what these things are so useful for. So you might wonder, like, why do we care about these things? This is kind of an esoteric thing. So let me tell you 2 reasons we care about them. One is, first of all, understanding space weathering. So space weathering, again, seems like a little bit of a special topic, but the only way we know what anything's made of, short of getting a physical sample of it in a lab, is by looking at its spectra. So the spectra, that you get these like wiggly lines that are characteristics of different, tell you that there are different minerals absorbing different kinds of photons, right? And so the space weathering process changes the optical properties. So it makes surfaces dark, at least on the moon. It depends on the kind of target surface, but on the moon, it makes the surface darker over time. It makes the spectral continuum slope redder, and it also erases those spectral absorption features. And so if space weathering is corrupting the signatures of stuff that we're trying to look at out there, it's important that we understand how that works. Mm-hmm. So that's why understanding space weathering is important. And then understanding lunar magnetism is important because, first of all, planetary magnetism in general is like a really fundamental thing. We talked a lot about this earlier. You have the fact that you have a magnetic field, or you ever had a magnetic field, tells you a lot about the deep internal structure of a planet. It tells you that it got hot enough to melt for the metals to segregate out towards the center. It tells you that the interior was hot and in vigorous enough motion to generate a magnetic field. It's like, it tells you kind of a lot of the story of the thermal history, the formation and thermal history of a planet. So these are 2 important things. And swirls are kind of this interesting little weird feature that live at the intersection of those 2 fields, and they give you clues about both. So this is a long answer to your question, but the shape of the swirl, I think, has to be telling you about the structure of the magnetic field. They have to be related, and I can give you some arguments for why, but basically it's telling you about those underlying magnetized source bodies, which in turn tells you something about how strongly magnetized they are, which in turn tells you something about the field that magnetized them. So maybe that tells you something about the thermal and magnetic history of the moon. And then at the same time, because we know something about magnetic fields, this is allowing us to learn something about the optical effects of solar wind related space weathering, because micrometeorites don't care about magnetic fields, but solar wind does. Mm-hmm. And so the fact that magnetic fields like these crustal magnetic anomalies separate those 2 effects allows us to understand space weathering better, which helps us understand basically everything that we're looking at.
Yeah. So does the optical properties of space weathering that you're talking about create that kind of like light and dark banding on lunar swirls?
Yeah, so the idea is that if there was no magnetic anomaly, you open up a fresh crater, it's bright material initially, and it will get darker over time as it's exposed to the space environment. Some of it is like glass is being created by these impact melts, and some of it is just like sputtering that happens when solar wind is hitting the surface. There's a few interesting things that happen. Like one thing that happens is like you basically vaporize bits of this rock, and there's like iron oxides in the rock, and the oxygen escapes from that little vapor cloud, and then the iron condenses into these little beads of metallic iron that coat the surfaces of the grains of these dust grains. And so you can look at this in the laboratory. They can do this with transmission electron microscopy, and you can see this happening, and it changes. That's what's responsible for at least some of the changes of the optical properties. Yeah. So what we think is that things are getting darker and all that. So the places where you see bright splotches that swirls are places where you're protected, relatively speaking, from the solar wind. So the idea is that and we can confirm this to some degree with observations that the dark lanes, the dark parts of swirls, are places where the magnetic field lines are open or vertical. So basically, particles are going to funnel down those magnetic field lines and hitting the surface and darkening it normally. Yep. But then the bright places are where the field lines are kind of more horizontal at the surface. They're essentially shielding, protecting the surface from exposure to solar wind.
Wow. That's super, super cool.
Yeah, right?
Yeah. That's...
There's a lot of... I just dumped a lot of stuff on you.
No, yeah, it's cool. Yeah, I'm just taking a second to process everything there.
Yeah.
So... I'm curious about, obviously there's like I don't know how valid of a hypothesis it is in actual research, but the hypothesis I laid out, which you have some kind of impactor that's
Oh, yeah.
magnetized, and it hits the moon and kind of gets buried over time. Is there any other hypothesis for how a magnetic body forms under the
Yeah.
surface? Maybe some kind of intrusive
Yeah,
magmatic thing, or
Right. So it could be intrusive features. So you have some kind of eruption or some kind of magma that comes up and doesn't reach the surface and makes an intrusive body and is somehow rich enough in magnetite or whatever that it acquires a magnetic signature more so than the surrounding country rock. That's one idea. And that's an idea that we suggested in this paper a few years ago because it's a good way to account for the morphology. Like, these things have these interesting characteristic swirly kind of patterns, and they look like kind of sinuous structures like you would get from like underground lava tubes or dikes in certain cases. They're long and narrow. So that's why we like that. But it's hard to think about how you get them to be so rich in, the magnetic minerals to be able to acquire a very strong magnetic signature. So that's where the metal hypothesis is good, like metal-rich impactors is good. It's harder to explain the morphology. It's not so obvious why you would make, long sinuous features with ejecta. Maybe you could do that a little bit with like ejecta arms, but they're not sort of organized radial to any impactor site. They're much more
ejecta arms. What is
Oh,
that?
I'm sorry.
Yeah.
When an impactor hits, you get like material flying off in all directions, and sometimes you get these sort of like linear type features sort of radiating out from the center of that impactor site.
So if you throw a Lego on the ground, you're gonna get those pieces of it kind of spread out over the ground
something like that.
Okay,
Yeah. But sometimes they organize themselves into they pick a certain azimuth, and a bunch of them will follow that.
Yeah.
But that's all I meant by that. But yeah, it's hard. It's very hard to explain these things, honestly. So yeah, maybe they're magnetic intrusions, maybe they're ejecta. Another problem is if they're impactors, they should be shocked, or they may be shocked, and that could do two things. One, if they were magnetized before, that may demagnetize them. Or it could be that nothing's magnetized and there's no magnetic field present in the first place, but the shock creates a brief magnetic field. There's shock magnetization. But on the other hand, some of these features are big enough that they shouldn't be able to, like, they must have cooled slowly. It's if a big object cools slowly, it takes millions of years to cool. And then if this transient magnetic field is only around for a day or something like that, it's not enough. And so that's why many of these kinds of examples favor a presence of a long running, like a dynamo that's operating, a global scale magnetic field generated in the core of the moon that's operating for a long period of time, hundreds of millions of years. Yeah. And that these are events that are happening during that time. But yeah, whether they're magmatic intrusions or metal-rich impactor ejecta that somehow gets obscured so you can't tell where it is from the surface, because these features, I should have mentioned this, but these features have basically no topographic signature at all. They're just look like they're spray painted on the surface.
Oh, really?
Yeah.
Wow. So, yeah, I mean, I'm a little perplexed on like how.
Yeah, me too.
Like, how do you form a body in such a way where, because I would imagine if it's an impactor, then maybe you could say that it was permanently magnetized in some direction in some other part of the solar system where it had the conditions to do so. But if you are on the moon and you're saying that there's no evidence for a magnetic field ever on the moon that's generated within the moon, then how do you end up
Wait, who's saying that?
No, just anyone.
Okay. If you say that. Okay.
Just hypothetically, right? And so how do you generate the orientation and in the permanent magnetization of that magnetic
that's a good
magnetic
question.
body to create a shape like so?
I think I see what you're saying. And I think it's a good question.
I didn't word that very correctly.
No, but I think I see what you're saying. Like, if it's just random material and there's no global dipolar magnetic field on the moon, then how do you get a coherent magnetization of that collection of rocks?
Yeah, exactly.
Yeah. No, it's a good question. It could be that, I think one of the ideas about this like impact generated plasma temporary magnetic field is does have some structure to it. So it has a particular orientation, but for a short period of time. And if it's intense enough, it may be able to magnetize these samples in some kind of coherent way. But yeah, honestly, I don't know. I don't know where the proponents of those ideas, haven't talked to them lately and heard if they've like got a good explanation that satisfies all the observations. I mean, I'm in the camp of favoring a dynamo on the moon, that there was a dynamo at the time that these things formed. And so then it's just thermal remnant magnetization. But I'm still left with the problem of like, okay, still, what are these things? Are they intrusive features? Are they ejecta or what?
Yeah, exactly.
Yeah.
So, Dr. Hemingway, I think that's all the time we have today.
Okay.
Thank you so much for coming on the show.
Yeah, no.
I want to give you a couple minutes here at the end to talk about any new research you have going on or anything you want to promote, or where can people find you and maybe ask questions?
Okay. Yeah. I mean, I don't really do social media or anything like that, but you can go to DouglasHemingway.com if you want to learn more about me or get in touch. But yeah, in terms of research, as you can tell, I work in a lot of different areas. So it's hard to kind of pick one to focus on. I mentioned that Venus project. I think that's something I'm kind of excited about right now because I've just come off just trying to understand why Venus doesn't have a magnetic field compared to Earth. And then, yeah, I think there's a lot more work to be done on icy ocean worlds. So that's another big area for me that I'm going to continue to work on for quite a while, I think. Just understanding the dynamics of those ice shells and what we can learn about the similarities and differences across these kinds of bodies across the solar system. Mm-hmm. But yeah, I'm sure there's many other things, but there's no time to list them all now. Yeah.
Gotcha. Well, thank you.
Yeah.
Appreciate
okay.
it.
No problem. Cheers.